University of Michigan engineers create centimeter-sized robots capable of more than ever before. Origami principles can unlock the potential of the smallest robots, enhancing speed, agility, and control in machines no more than a centimeter in size. University of Michigan researchers have demonstrated that behavioral rules underpinning the Japanese art of folding can expand the capabilities of these machines, creating potential for greater use in fields as diverse as medical equipment and infrastructure sensing. Their bots can form one shape, complete a task, then reconfigure into a second shape for an additional task, and so on. The latest research from the team appears in the journal Advanced Functional Materials. To date, most microbots have limited movements, which hampers their ability to perform useful tasks. To increase their range of motion, they need to be able to fold at large angles. UM's team has created microbots that can fold as far as 90 degrees and more. Larger folds allow microbots to form more complex shapes. UM's unique approach enables its microbots to complete their range of motion up to 80 times per second, a faster pace than most can operate. Microbots using origami principles often require an outside stimulus to activate, such as heat inside a body or a magnetic field applied to the microbot. UMs utilize a layer of gold and a layer of polymer that act as an onboard actuator, meaning no outside stimulus is needed. While the microbots are currently controlled by a tether, eventually an onboard battery and a microcontroller will apply an electric current in the systems. When current passes through the gold layer, it creates heat, and this heat is used to control the motions of the microbot. The initial fold is driven by heating the system, then unfold is done by letting it cool down. Overheating is done to get something to fold and stay folded. These capabilities allow microbots to function elastically and plastically, giving them the ability to recover their original shape. Combining the elastic and plastic folding enables these micro-origami to first fold plastically into a desired geometry and then fold elastically to perform a function or for enhanced shape mobbing. The proposed origami systems are suitable for creating medical devices, metamaterials, and micro robots where rapid folding and enhanced control are desired.